Yeah, then welcome back to Fall Methods for Software Engineering. We had some slides left from the lecture. So the last part that we started was model checking and LTL specifications. So we looked at how do we write LTL specifications for models in newer XMV. And we had this example here where we put this LTL formula that globally, if there is a request, so basically every time there is a request, that's what the globally means. This will imply that after some finite time later, we will have the assignment state equals busy to be true. So the system will go into the state busy instead of ready after some finite amount of time or even immediately. And then we could check this, and we could also see what happens when a property does not satisfy, when a path doesn't satisfy the property. And we got those counterexamples. We looked at them the last time. What do they mean? And then we checked that even different models. So here we added some non-determinism. On the left side, it always goes to ready if there's no request, but on the right side, it might remain in busy as well. Could go to ready, but it's not required to do so immediately. Then still the LTL properties, they might still be satisfied. So there might be many models that satisfy some LTL properties. And of course, there will be many models that violate some LTL property. And here we were looking at, this is the new thing, so the slide that we didn't do last time. We saw that there are different ways to describe the transitions in the model. So we said a model in model checking, this is always a transition system. And we define the possible labels for this transition system as the variables in new SMV. So here, the labels of possible states are valuations of these variables. So whether coin is equal to true or equal to false, whether amount is 1, 2, 3, 4, or 5. And you can, how many states could we have if we have these variables determining our states? So how many different states that are different in terms of the labels of, well, in terms of the valuations of variables? 12, why? Yeah. 6. Yes, so the states, if we just look at the variables, then the valuations of the variables are completely independent of each other. We have 2 possible values for coin, 6 possible values for amount, so that's 12 possible combinations. So that's 12 states that we could have in our system. And then we saw that we, of course, need to say what are maybe the initial states. If we don't say what are the initial states, then any of them can be an initial state. And then we need to say what are the possible transitions. So from what state can we go to what other state? And we saw that this can be done with the assign, which is like we know it maybe from many programming languages. We say the next value of amount, we assign it the minimum of 5 or amount plus this coin value evaluated as an integer. So if this means that if coin is false, then this true integer will be 0. So the amount will either be, 5 if it is less than the amount, but amount can only go up to 5. So if amount is 5, it will always remain at 5, no matter whether coin is true or false. And in all other cases, let's say amount is 0 and coin is false, what value will we have in the next state for amount? Amount currently is 0. Coin is false, so this means it's 0 plus 0. And the minimum of 5 or 0, that's 0. So the next value will remain 0. That's this kind of assignment here. And if it's let's say the amount is already maybe 2, and coin is true, then there's 2 plus 1, that's 3. And the minimum of 5 and 3, that's 3. So the next value will be amount updated by 1 because coin was true. So then next value of amount will be 3. Okay, now let's look at a very different formalization. We said there's the assign blocks, and then there are trans blocks. And the difference between the assign block And the trans blocks are that in the assign block, we usually write assignments. We say this variable will get this value. In the trans blocks, we just write constraints. So we just say this is some constraint that needs to hold for all transitions. How do we see that there is a transition here? How do we see that this describes actually moving from one state to the next in this trans block? How do we see that it's a transition? So the indicator that this is actually a transition is this next keyword, because we are relating a current value to a next value. That's the same as we did in this assign here. We are relating the next value, so let's say the successor state value of amount, to the current value of amount and the current value of coin. And here in this constraint of in the trans, we're doing a very similar thing. We are saying that the if we currently have a coin, this implies that the next value of amount will be, well, amount plus 1 or 5 if we are already close to an overflow of this data type, right? So here, next amount would be amount plus 1 if there is a coin, right? So now we have some LTL property here that always globally finally or always eventually, if there is a coin, then we will have at some point in the future, and from that point on forever, we will have the amount equals 5. So this basically means if you put enough coins into the vending machine, then the number of coins will reach 5 and stay 5 because there's no way to decrease it, right? If we put no coin, then amount will still stay 5, right? So let's check this property. Here we go. Oh, by the way, the syntax highlighting now works out of the box again. So thank you, Shoaib. Yeah, so let's see. This is our specification. Let's run this. And it says the specification is true. So indeed, that if we put in enough coins, then we will end up at having 5 coins forever. So let's look at the other one, where we use the trans instead of the where we use the trans instead of the assign. And then we said if there's a coin, then we will increase the amount by 1, right? If we do run, let's say we compare it to this one, where basically we only changed from this assign to this trans. Will it say the same output? Is this same LTL formula still satisfied? What we're asking here, whether this is satisfied for any possible computation in this model. We don't have initial states, which means that we don't have a constraint on initial states. So any state whatsoever would be an initial state. That's fine. Like we had in these examples where we said, well, we have a bunch of states. Any of them could be initial, so we can write down all the computations that happen from those states. And here we already saw we have our 12 states. And then you can imagine that we can start in any of these 12 states. We can start our computations. And then the successor states, they are, well, somewhat determined by this transition constraint, but there are still many. And there are still infinitely many computations because the computations are infinitely long, and we can just play with coin on and off. So we can have infinitely many computations here as well. And it will check all of them, whether they all satisfy this. That's what the model checker does in the background. So what do you think? Will we get the same result? If there's a coin, we have to increase the amount by 1. You want to look at the previous one. Should we just check it? Any opinions? Who thinks that it will say the same here, that the specification is true? Who thinks it will say the specification is not true?
Maybe the one here has something to do.
The +1?
Yeah, because there's a Boolean conversion in the previous.
Ah, okay. So you think it's better to write to int of coin? Yeah, maybe. It's the same because we know if the left side is true, then it must imply that coin is true. So this is +1, right? Okay, but yeah, let's write the same way. Do you think that now it gives the same result? Okay, let's just run it. I mean, it's difficult to think about this kind of stuff. Let's just run it. It's not the same. Huh. Okay. Well, it gives us a counterexample, right? It says the specification is false. So we feed it coins, but still we're not going to end up at the amount of 5 coins in the end. So yeah. Why? It tells us why. Whenever a property is violated, we get a counterexample. The counterexample will show us a computation. Is this an infinite computation? Well, actually, how many states do we see? 1, 2, 3, 4 states. But there's a loop around all of them. So it basically says after you have done those 4 states, you're going back here and do those 4 states again. So it's an infinite computation because it has a loop. So all these will have loops if they're they must have. That's definition basically. So what's the problem here? Now that's what you will be confronted with in reality, at work, in industry. What happens is the property that you think is correct, or the model that you think is correct, they're not. And now you have to figure out why. And here is why. That's the counterexample. So what you now need to do is you need to think about this counterexample guarantees that it follows everything in your model. There's not many stuff in our model. There's stuff like what can the variables be and what are the transitions. So we only have a single constraint. That's very nice. So we can now maybe just understand, does it satisfy this constraint? But it guarantees that it does. So yeah. But we should figure out how does it violate this, right? Because this is what we thought would be true, that this would be satisfied by all computations, but there is one that doesn't. So yeah, now try to explain why this is not satisfying. So usually, if something is not satisfied, there is maybe some behavior going on in the computation that you didn't think about. So if you just read the computation and explain what's going on, so let's say this is a vending machine. What is somebody doing with a vending machine? So what can you operate? You can operate the coins and you can operate the amount. Okay, so let's say I'm the vending machine. I'm updating the amount. And one of you is the coins. Who wants to be the coins? So I'm the vending machine. I say my amount is 0. So one of you says you're not putting in a coin, right? Then next state doesn't mention amount, which means that it remains 0. Okay, so I say, well, I'm 0 again. Now one of you says, well, here's a coin. Then I say, well, there's a coin. So of course now coin implies I update my amount, right? So now I say my amount is now 1. And you guys say, this time you don't get a coin. And then I say, then I set my amount to 0. How can I set my amount to 0? Am I violating this constraint here? Coin is false, right? And that's an implication. So if coin is false and this is an implication, I'm satisfying this, right? There's nothing for me to do here because coin is false. So I can take amount, whatever I want. There's no constraint now. This is satisfied, this constraint here. So I can just say, well, I take amount 0. And then we're back here. You tell me there's no coin. I say my amount stays at 0. You tell me there is a coin. I say, okay, my amount is still at 0, but in the next state, my amount is 1 because you gave me a coin. And so on. So we're always alternating between amount 0 and 1. So now let's see. Does this satisfy the LTL specification? Globally, finally, coin. That is true, right? And this eventually, globally, amount equals 5. That's not true because we're always alternating between 1 and 0. So we're never even reaching 5 once. So this specification is violated by this example. So how do we fix it? There's obviously a problem in our model because something happened that we didn't think about, right? We didn't think about the case that when coin is false, then what should happen? What should happen? Let's say well, yeah, so coin is false, so we can just write not coin. Oh. This then implies that something with the amount, right? Amount equals amount? Yeah. So one of them is the next, right? We want to say the next amount equals the current amount, right? Okay, so I think we might have to do another. Yeah. So what happened is that we terminated this block with the semicolon, so you can only put one expression in the trans. So if you want multiple ones, then you write multiple blocks, multiple trans blocks. We could have written like parentheses around this and said end this constraint, but that's the same like in SMT you had multiple asserts, right? And each assert would have to start with the assert keyword. So here, yeah, if you have multiple trans, you can write them all with the trans keyword. Okay, now we are handling also the case where coin is false, and then we're keeping the amount the same. So yeah, and now the specification is true. Okay, so we fixed this model. Because now it's like what we expect. The vending machine should, if there's no coin, it shouldn't forget that it ever had coins, right? That's not nice behavior, but that's actually something that can easily happen when you use this trans block. Because there you're just writing constraints and you might only think about the constraints that you definitely want to be true, but not the ones that you are maybe implicitly expecting to be true. But how would, so from, let's say, normal programming languages, you would expect if you don't assign a new value to a variable, then it won't change its value. But that's not the case here, because here, these are constraints over variables. If we don't constrain the way that the variables change, then they're unconstrained and they can change in any way. So in the case where coin was false, we put no constraint on amount. So it could be whatever it wants to be. It could even go to 5 or 1, 2, 3, right? It can go to any value it wants. In the counterexample that we saw, it went to 0, but that was just, yeah, because it could. Okay, so there's some difference between this assign and trans. When you do assign, you're a bit more on the safe side, that you really catch all the cases, because you always will, your right side will always evaluate to some value, right? So every variable that you put in the assign block will have some value in every state. The tricky bit is that when you maybe have some variables and you don't know all the cases in which they might change their value, then you would still have to encode all these cases into the right side of the assign, which might be a bit tricky. It might be easier to do this with the trans block, because then you just write different constraints that you want to be true, and the combination of all these constraints is all your different cases. So you don't have to like come up explicitly what are all the things that influence the value of amount, and then put them all on the right side here. With the trans, you can say, well, the coin influences amount, maybe no coin also influences amount, maybe the reset influences amount, stuff like that. You could all write in different trans blocks, and that's why people have both options here. For stuff where yeah, everything that influences it, I can write it on the right side here, then I use the assign. But if I specify it more openly, then I can use the trans, because I just write constraints. Okay, so let's look at some classic problems from mathematics. Anybody ever heard of this 3n+1 problem, or the Collatz conjecture? No? Ah, okay, yeah, it's a very famous conjecture. So there's a very simple function. This function has two ways to evaluate. Either, so it takes an integer, and either it multiplies this integer by 3 and adds 1 in cases where the integer was odd, or in case the integer is even, it simply divides it by 2. So this function is very simple, right? If the integer is even, it divides it by 2. If the integer is odd, it multiplies it by 3 and adds 1. Now, the conjecture here is that if you define a sequence where you take any number, you apply that function. That gives you again an integer. So you apply that function again. And then again and again and again. So let's start with maybe the number, I don't know, 2. We see that 2 is even, so we divide it by 2. That leads us to 1. And the conjecture is that we always end up at 1, no matter what happens. If we apply this long enough, we'll always end up at 1. So let's take number 3. So 3 is odd. So we have 3 times 3 plus 1 is 10. Now, 10 is not yet at 1, right? So let's take 10 and apply the function again. What number do we get applying this function to 10? 5. Okay. Let's apply the function again to 5. What number do we get? 16. Let's apply that function again. What number do we get? Let's apply it again. 4. Let's apply it again. 2, 1. We reached 1. Okay. So now we tried it for a few numbers, right? And it worked. So, but how do we really show that it works for everything? So now maybe take out some paper and some pen and try to prove that it works for everything, and then hand in this proof. Nobody's writing this proof. There's even, so this conjecture turns out it's not that easy to prove. It's a bit difficult to prove. So there's even some, this comics, XKCD comics? So there's even some XKCD comic about it. So the Collatz conjecture states that if you pick a number and it's even and divided by 2, and if it's odd, multiplied by 3 and add 1, and you repeat this procedure long enough, eventually your friends will stop calling to see if you want to hang out. So yeah, and that's basically describing this procedure, right? But it's a difficult way to prove it. It's not so easy. If you can prove it, you'll probably get lots of money, because there are even some companies that promise some cash prizes for proving it. So please hand in your proofs by the end of this lecture, and you'll get your share. No, so basically, yeah, it's been a problem that's been unsolved for quite some time. So let's try to encode it in USMV. Let me just so let's try to encode it. What we want to say in the end, that our number n or x, whatever we call it, reaches 1, right? And we say after some finite amount of applications, because you don't want to apply it infinitely many times. So after some finite amount of applications, this reaches 1. That's our conjecture, right? Or not ours, but Collatz conjecture. And then we need to encode this function. How do we encode this function? Well, we can simply say every state has some number, that's some integer number in every state. And then we only need to encode how this number changes, right? Because we want to encode the element in a sequence. We could use this assign, and then we want to start by some initial value. We say x equals, well, we tried the 1, we can try the 3. We tried the 3, right? Yeah. So let's start from 3 initially. And then how do we update the number? We need to encode now in USMV what happens. So the case that it is even, so if we divide it by 2 and the remainder is 0, then it's even, so we just divide it by 2, right? The other case, it's odd. I don't know why we even have a last case. Not really. We probably don't really need this case because they should be exhaustive. But yeah, anyways. So if it's odd, and now we have to kind of, yeah, we have to deal with this overflow again in one way or the other. Let's just pretend there's no way to overflow. So if it's odd, then it's 3x plus 1, right? That's why we needed the last case, because it could be that we actually do not satisfy that we are. So the problem is in USMV, we always have some upper bound, right? So this upper bound, we need to encode it because our integers are bounded. So we would want some integer, x, and that should start, well, probably at 1 and goes to, well, this maximal number, right? And then we need to, of course, define a maximal number. So let's pick, I don't know, 100 as a big number, right? And now let's see, is it true that if we start from x equals 3, that eventually we reach 1? Yeah, it's true. So we showed that it works for starting from 3, right? Does it work for starting from 4? Well, we already had that in our sequence, so yeah, that's going to work. 5, I don't know, did we have 5 in our sequence? Not sure. Yeah, also works. Great. But actually, so let's go back to this one because we did that manually, the 3. Can it give us, how can we trust it? Can it show us how it did that? What can we do with this thing? It can check whether some LTL specification is satisfied. Yeah. What happens if we negate it? Then it should do what? It should find a counterexample. So if it finds a counterexample, this counterexample is a computation that, of course, has to start in the initial state. And then what can be the next state? The next state must follow the function application, right? 3 times 3 plus 1, that's 10. 10 is even, divided by 2, it's 5. Then we go to our 16, then we go to 8, then we go to 4, to 2, to 1. So now we are actually using the model checker in a constructive way, because we're telling it, well, give us a proof or give us the way that you calculated this. Okay, so this would be the evaluation of those functions. Now, but that's not so nice because we again show it only for some sequences here, right? So let's check. How do we check that it works for any number? What happens if we remove this initial constraint? Then what number can it start from? Any number. Yeah. And if among those numbers it finds one that doesn't end up at 1, then we know that the Collatz conjecture is false, right? So let's try that. Seems to be true. Is there a catch? Can we claim the prize money? Why not? Yeah, we did it only up to 100, right? So starting from any number less than 100, we could show that it works, but that's not what the conjecture asked for. The conjecture asked for any number. So let's try to increase that. Let's try 1,000. 1,000 also works. Try 10,000. I mean, 10,000 is a large number, right? And you can imagine that it has to check all the sequences, right? Because it's true. Good. So 10,000 still works. We're getting closer to the money, right? 100,000.
Also, our overflow case, we're gonna leave some cases out just because of that. 3 times x plus 1 is like
Yeah, so what we have here is we have this case in case it would overflow. We're not doing this assignment, so we're not following the sequence, but we say just jump immediately to 1. So we're cheating a bit, like because even with starting with, let's say, I don't know, small numbers, I'm not sure which number, maybe 7, the sequence would already get us above 100, right? We don't know because we haven't checked it manually. So here that's a bit of cheating. The idea is that if we get an overflow for a smaller number here, we can always increase that number and see if we hopefully then don't get an overflow. But yeah, we should probably we could how do we okay, so with 100,000 the process timed out after 60 seconds, so we now have to ask Schoip to increase the timeout for us. But yeah, that's not going to get us the money, right? Because we always have this limit of boundedness. Okay, how do we fix this overflow thing? Is there a better way to deal with the overflow? Here we're just saying, well, let's kind of ignore the overflow for this range of numbers. Hopefully that's safe. But we could also maybe explicitly find it. How do we find this overflow? How do we check that there is an overflow even? Maybe every number we pick, it fits here. Okay, let's go back to 100, then it's a bit easier. So how would we check that we don't get an overflow up to 100? Every number we pick and we develop based on the sequence, we never get an overflow. How do we check this? Let's now write a spec for this, right? LTL spec. We don't get an overflow, right? How would we assert that we don't get an overflow? That we don't get it, this would probably be something like globally. We could state this with globally. And then, yeah, what does it mean to get an overflow?
calculations over the that's gonna be
This thing here could give us an overflow, right? So that's we're saying we will always be that 3x plus 1 is less or equal to the maximum. Then this means we don't have an overflow, right? If that never happens, so this one, x divided by 2, we can't get an overflow because it decreases the number, but this thing increases the number, the 3x plus 1. So let's see, do we get overflows? Okay, so it says it is false, so we get overflows. And it shows us one way to get an overflow. If we start from number 80, then we might get an overflow because wow, even we go down to 5, then 16, 8, wait, where's our overflow? Yeah, okay. So this thing doesn't really overflow, right? We made a mistake in our LTL spec. Why? Of course, 3 times 80 plus 1 is larger than 100, right? But we don't care about that because that is an even number. So actually, we need to extend our overflow detection a bit further. We actually want to say that the number is odd, and so every odd number, so we could say number is odd, number is odd. This implies that 3x plus 1 is less than the maximum, right? So because if the number is even, we don't care. Only if it's odd, we care. So let's see. What? If the number is odd, did we... Let's take 99, right? 99 is definitely odd number. And 3x plus 1, that's really large, right? How come that is less or equal to m num? Less or equal to 100? Oh, it's how the operators bind. It's how the operators bind. Globally binds the left side here. So it says globally an odd number would imply this, but globally an odd number is simply false because the number will never stay odd, right? So we actually want to say globally this whole thing, not globally an odd number implies that other thing, right? Now, yeah. Okay, so now it's false again, that's good. We can start at 60, we go to yeah, here, 30, then 15. Okay, 15 times 3 plus 1, that's 46. Then again by half. Then you mentioned 35 before, right? Yeah, and then from 35, yeah, well, 35 times 3, that's how much? That's already 105 plus 1 is 106, right? So yeah, very good. Okay. So now we made many mistakes with even writing LTL specifications, but now we figured out, yes, we do have overflows, so this handling is necessary. I mean, we all knew that we have overflows, right? Just because you can take a very, very large odd number and then times 3 is definitely higher than this 100 pound. Okay, so we're not going to get the prize money because our check only goes to some defined number, so that's not really good enough, and I don't think we can solve it with this model checking, right? There might be other ways to solve it computer-based, but this is not the way to solve it, sadly. Okay, yeah, and then we saw how do we use counterexamples as solutions. So we could say if we initially start at 123, then globally we're not reaching 1. This is the same as not finally x equals 1, right? That's what you suggested. We simply negate it, and then we get a counterexample. And instead of putting this initial value into the model, we could simply put the initial value into the LTL constraint. Maybe that's a bit cleaner. And then you would get a counterexample. Well, not a counterexample. You would get an example of the sequence that it really ends up at 1. Yeah, like that. This is how we can kind of constructively use counterexamples to see how to get to some desired solution. Okay, now a quick reminder about LTL equivalence. So when we looked at the first part, before we looked at model checking, we looked at LTL. And then we had some LTL formulas where we said, yeah, these might be equivalent. They might actually be satisfied by, for all models and all paths. If the path satisfies one formula, then it will also satisfy the other. So if it violates one, then it would violate the other. But if it satisfies one, then it must satisfy the other. So for any model and any computation path, the satisfaction values must agree in both directions, so they must be equivalent. And then we saw that there are different ways to address this. Anybody remembers how we addressed this, how we showed actually equivalence? Or anybody remembers how we showed that two formulas are not equivalent? The not equivalent was really a bit simpler, right? Because we could find a counterexample. What was a counterexample in that case? A model and a path, right? So if we find a simple model and then a path in that model where the two formulas evaluate differently, then we have a proof that these two are not equivalent. And we had this thing with eventually x and eventually y is not the same as eventually x and y. Because in eventually x and y, they have to, sorry, I have, we showed this difference between two formulas where we said eventually x and y, this means x and y must happen in the same state or must be labels of the same state, and the eventually x and eventually y just means that they both have to become labels of some states on some computation path, which is different. So now, can we use a model checker for checking LTL equivalence? So let's maybe create a new spec. We always need a module main, right? Then we need some variable. So let's say we have p, which is Boolean, and q, which is Boolean. And then we want to say that maybe we have two formulas. So let's say p and q. And now let's make it very explicit by putting some parentheses. Let's do the same example that we did manually. So how would we express this in an LTL formula? When we looked at the two sides, we kind of looked at implication, right? So whenever a computation satisfies this, does it also satisfy that? And whenever it satisfies this, does it also satisfy that? Can we use this again? So let's see if we say this implies this, and just to be, now we basically have the left formula implies the right formula. But should we check this now? We don't have a model yet, right? So anybody remembers this model that we had? We had two states, I think. And one state was labeled P and the other one was Q, right? So how do we encode a model like that? So we have to say something in the initial state, right? Can we say P is not Q? Is that syntactically valid? Or does it not work with Booleans? Okay, but that's not really all of it, right? So how do we write the transition? What are the possible transitions? We have to write again a constraint that makes sure. So right now, we say that initially the value of P is not the value of Q, which means that one must be true, one must be false, because there are no other ways. So the initial states, we only have P and not Q, and we have Q and not P. So the initial states were fine. We have two initial states. How do we make sure that we also only have two possible next states, right? So we basically can write the same again, and we can say next of P is not next of Q. Now we have made sure that also all the successive states are disjoint, right? That we only have those two successive states. So now initially we only have two states, and now on every successor we also only have two states. And now we said that we want this transition that goes from P to Q, right? So how do we write that? If we are in P, then next we must be in Q. Yeah, and we can write even another one. If we are in Q, then next we must go to P. So that's now we rebuilt our manual model that we created, and now that's quite interesting. Here we have actually three different constraints. One we just used to restrict the possible states that there could be, and then those two we actually used to really introduce the transitions, right? And then we can see that this specification here is true. Why is that true? Didn't we say it's not equivalent? Or we only showed one direction, right? We showed the direction that if eventually P and Q, which shouldn't hold here, can we check that it doesn't hold here? Let's check that it doesn't hold here, right? Let's also check that really the left side doesn't hold here. Yeah, so our intuition is correct. So we only showed, let's say, one direction here. Now let's do the other direction. Take that stuff and move it to the right. So let's check the other direction as well. And now the other direction is false. So if we have eventually P and eventually Q, this does not imply that eventually P and Q. So just to check our intuition again, we said that in our model that we manually crafted, eventually P and eventually Q are true, right? So yes, it is true. Good. And so we showed that the left side is false, right side is true in this model, and then of course the right side cannot imply the left side. So we get a counterexample here, and that's yeah, well, this alternation between P and Q states, right? That's simply we start where we only have the label P, then we move to where we only have the label Q, we move to P, we move to Q, and so on, because it needs to be an infinite computation. Okay. This way we can show that the two are not equivalent, but we still had the manual effort of coming up with this model, right? And that's not so easy, not so nice. What if we wouldn't write anything here? Do you really have no model? Is it really no model right now? I deleted all the init and trans. Do we really not have a model? Do we have initial states? Yeah, we do have initial states. What are the initial states? Yeah, can be, well, almost anything here, right? Any combination of P and Q labels on states. Do we have transitions? We didn't restrict them. We have states. So we have unrestricted transitions. So every possible transition from any state to any other state, that's a transition. So we have like a maximum model here. This model can do whatever it likes. Now, what happens if we check these LTL constraints? These implications here. Will they be true or false on this model? So this model can do whatever it likes. This means it can produce any possible computation over these variables P and Q. It can. Is there a model that can produce more computations than this model? No, because any other model could only produce less computations than this model here, or the same number of computations if it's also unrestricted. So this means that we can simply check our LTL constraints on the unrestricted model, because that includes all computations. And we only need to find one that violates them. And if there's one that violates them, then it must be in this unrestricted model. So we're going to find it. So let's check. The left side here is again true. And that's very good, because now we show that this implication actually doesn't only work in one model, it works in all models. And the other one here, the basically going from this side to the left side, this is now again false, and we get a counterexample. So now we find another trace where, for example, we start with P true, and then Q true. That looks very similar to what we had before. And then it will set Q to false. So now both are false in this state. That's it. Okay. Okay. And then this state here doesn't change anything because it doesn't mention any variables. So this means it will stay false forever. And that means we have satisfied eventually P, because we satisfied that in the first state. We have satisfied eventually Q, because we've satisfied that in the second state. And we haven't satisfied eventually P and Q together, because, yeah, from now on everything is false forever. So, yeah, that's it. So we can actually check equivalence between LTL formulas by checking them with the model checker on the unrestricted model. The only important thing that we have to do is we have to declare all the variables, because otherwise we wouldn't have a model that matches the LTL formula. Okay, yeah, so here, that's basically what the model checker does. It takes two formulas on a model M that it has given, and it checks whether the path is basically satisfying the formula. And here we were asking for two LTL formulas and all models, and then we can take the unrestricted model. So find all possible paths by simply using an unconstrained model. Yeah, and then this is the ones from the slides. So from the in the slides we had this check whether this globally and the for the conjunction works, and then whether the globally for the disjunction works. And anybody remembers the results? So if we have globally A and B, is that equivalent to globally A and globally B? So in all states, A and B are true. Here it says in all states A are true and in all states B are true. So that's equivalent, right? So with the end, this globally and the end, you can split that up and it's still true, but the or not, because you could have globally A or globally B by having A and B alternating, and that's not the same as having A always and B always, because here you could just have either one of them always. So that's why these two are not equivalent, and we can see this, probably we can see this alternation here. Here A is true, then A becomes false. This means B should be true, right? Yeah, and B becomes true. And then we have, wait, we have the initial state set of the finite state machine is empty. How come? Initial states of the finite state machine is empty. We don't have any restriction. Maybe that's part of the model checking. Not sure why we get this warning here. Maybe that's. I'll check why we get this warning here. Usually you get warnings like this if you have, for example, some initial constraints that say false or that implicitly are impossible to satisfy. And then you get this, and this is usually a very serious thing to get. But here we might get it because of the construction that is created for the model checking. Can this be? Yeah, I'll check why we get this. Usually you shouldn't get these things because they mean that something is odd, but maybe for this equivalence checking, we might get them due to the construction of the stuff that it does in the background for calculating the equivalence. Okay, that's the that's basically the globally and the and or, and then the eventually that we already used as a running example. We saw that here we have eventually A or B. Is that the same as eventually A or eventually B? And then eventually A and B, is that the same as eventually A and eventually B? So I think here we showed, yeah, the difference, right? So, no, sorry, the or is true. Why is the or true? Because, of course, yeah. If we have A or B, this means we just need to find a state that is either labeled with A or labeled with B. And then either we find that state, of course, again here, or we find that other state here. So that's why this one is fine, but this one is the one we used, which is false, which we used as a running example. Yeah, and here we don't. Here we also get this. So I guess this is a warning that comes when we construct. Is it for the true case or for the false case? Let's try that. Okay. So apparently this warning comes when the formulas are equivalent. Yeah. Okay. Yeah. So if you have equivalent LTL formulas, you might get this warning, and then it's fine. But in other cases, you shouldn't get this warning because then it usually indicates some issue. But I guess here it's a side effect of the creation of the state machines for the equivalence checking. Okay. It doesn't really make sense in this unconstrained model that it says that it doesn't have any initial states, right? Here we know it has 4 possible initial states. So yeah. Okay. Any questions about the equivalence checking? Oh, good. Then this was the solution for another quiz that we had on these implications, where the one implies the other. Yeah, just as a completeness, so we can now also handle this all automatically. Yeah, and that's it about the model checking. So now you can guess what will be part of the worksheet for the homework. Very likely you have to do some equivalence checking, right? Let me check. Yeah, so the worksheet, you first have some exercise where you just have to create some LTL formulas as a warm-up. Then we do these kind of semantic relations. So you do these analysis where the one formula implies the other and the other way around. So that's this thing. And then we have something where you get already the models, you get them. And you can try to understand the model. There's an LTL formula that is not satisfied. You have to read the counterexample and then in natural language explain why this LTL formula is not satisfied. So you basically have to read the counterexample, relate it to the model, and explain why this counterexample actually demonstrates that this formula is false. So and we can't check that in an automated way. We tried with like ChatGPT, for example, but it was just wrong too many times. So they're not very good at this. I mean, you can try this. We gave it the model, we gave it the counterexample, we asked it to explain it. That gave sometimes correct, sometimes incorrect results. And then we asked it to basically grade an explanation. And it was also sometimes saying, yes, this explanation is good, or no, this explanation is bad. But even for its own explanations, it said this is bad. So it was not in a way that we could have automated it for giving you automated feedback on this. So we will do this by hand, this feedback. So the test cases for that part, they will just, where's the, here. So the test cases for that part, they will just say you wrote something in this file, right? And then we will have to manually check it. And then the last one, you have to write your own encoding of some moves, how a knight on a chessboard can move. So here, this one, the knight can move here, it could move here, and it could move here. Those are the possible moves in one move. And then you have to kind of encode these moves. And here, for example, the white one could move here, or here, or here. So you just have to find a way to express this, how they can move either with an assign or with a trans. That's the part of this. There's a template again that already gives you the variables. So it just has an x and a y coordinate. And the first one of this array, so the array at position 0, that's the x coordinate, and the array at position 1, that's the y coordinate on the chessboard. Okay, that's the very quick overview of the homework. Any questions about this? Okay, good. Then you can try to get it running, and we're still here for 20 minutes to see if everything works.